Good morning, everyone. I see that the conference dinner was a great success because the room is filling up a bit slowly. This is usual after the ICAP conference dinner, and I'm very pleased to act as a replacement for Juni, for chairing this morning session on cold molecules and laser cooling of molecules. So it's a pleasure to introduce Dave DeMille from Yale University. We'll speak about direct laser cooling and trapping of diatomic molecules. Dave, please.
Hey, thanks, Christoph. So I'd like to start by joining all the other speakers in thanking the organizers of the meeting. It's really been a fantastic experience, one of the best conferences that I can remember, really very memorable. So thanks again to all the organizers. So as Christoph said, I'll be telling you in my talk about a series of results over the last handful of years where we've been learning how to do direct laser cooling and trapping of molecules. And I'll tell you both about work in my lab and an overview of what's happening elsewhere in the field. So I'll start with some motivations why we're doing this, then give some details about experiments, older experiments where we were able to demonstrate laser cooling and slowing of a particular molecule, strontium fluoride, and then most recently experiments where we've been able to make magneto-optical traps of strontium fluoride molecules, and then a bit of outlook at the end. So for those of you who haven't heard this story before, probably the first things that comes to mind is why would you even want to do this? So we know that molecules are complicated. In addition to the electronic states and fine structure and hyperfine structure that we're familiar with from atoms, there are additional internal degrees of freedom like vibration and rotational motion. Here, vibration is the large scale, rotation is the smaller scale. Other internal degrees of freedom for more complicated molecules. So clearly this is going to be more difficult than working with atoms. Why bother? And it turns out there are a lot of very strong motivations. One that's near and dear to my heart is that it turns out molecules are very useful for doing experiments probing fundamental physics. And in a nutshell, the reason why is that the near degeneracies of internal structure from the rho vibrational structure of molecules, near degenerate energy levels, gives enhanced sensitivity to perturbations from interesting new physics, such as new particles and fields. So one class of experiments that we've heard about earlier in the week is looking for time reversal violating electric dipole moments, such as the electron electric dipole moment. Jerry Gabriel's talked about our collaborative work on the ACME experiment to look for the electron's electric dipole moment using thorium oxide molecules. I'll mention a bit at the end, there's also the possibility to look for the proton's electric dipole moment. And the key point here is that molecules give you an enhancement of factors of 1,000 or up to 100,000 relative to similar experiments with atoms in searching for this physics, which is really at the cutting edge of particle physics today. But this is not the only example. For example, you can study properties of Z boson exchange by looking at parity violation in atoms and molecules. And again, molecules give an enhancement of a factor 10 to the fifth or more in sensitivity relative to atoms. And we, in a group in the Netherlands, are pursuing experiments to study these effects. And there are also a number of groups using enhancements in molecules to study variation of fundamental constants, such as the ratio of the electron to proton mass ratio. And again, molecules, because of the near degeneracies, can give factors of 1,000 or more enhancement in intrinsic sensitivity. So many of these enhancements have been known for many, many years, but it's only over the last decade or so that the techniques for controlling and measuring molecules have become sufficiently advanced to take advantage of these fundamental amplification factors. In addition, sort of in a completely different direction, there's a very strong motivation to use molecules to study many-body physics. And here the key point is that the polar molecules interact via electric dipole-dipole interactions, which are extremely strong and long-range and anisotropic. And I'll emphasize the strength of this. We've heard beautiful talks earlier in the week about dipolar interacting gases, such as using dysprosium or erbium atoms. Compared to even those very magnetic atoms, the electric dipole-dipole interactions in molecules can be hundreds or even 1,000 times greater. And that really will push these strongly interacting gases into a new regime where the interaction is the largest energy scale in the problem. Bigger not only than the mean field energy in a quantum degenerate gas, but bigger than the kinetic energy or the temperature. So there are many, many proposals for experiments that would use the properties of polar molecules to study interesting new physics, to do things like simulation of quantum magnetism, to look at exotic phases in strongly correlated systems. There's been a set of pioneering, absolutely beautiful and seminal experiments from the groups of Debbie Jin and Junyi at Yale using potassium rubidium molecules that have started to explore this space, but there's still an enormous amount to be done in this area. So one of the themes that you'll see throughout the talk is that with molecules, colder is better in almost every way. So for example, the internal structure of molecules, the rho vibrational structure, means that for any ordinary temperature, there's a Boltzmann distribution that spreads population over many internal levels. So when we talk about cold molecules, we mean not just cold in their motion, as we usually care about for atoms, but also cold in their internal degrees of freedom. But of course, these days we're also able to start controlling and cooling the external motion, the center of mass motion of molecules. And this is useful, for example, for precision measurements to give better spectroscopic resolution. And ultimately, as we're starting to get molecules cold enough, we're able to trap them. That again is the best possible case for precision measurements, but also gives you the possibility to fully control the quantized motion and become even more sensitive to weak interaction effects. So just as we've learned for atoms, there are new phenomenon control available at every new regime of temperature. So with that in mind, there's been a big push to create techniques to cool and trap molecules with the motivations that I've talked about, like quantum simulation, precision measurement, but a whole range of other things as well. And this shows what you need to do these sorts of experiments in terms of phase-space density and in terms of number of molecules. So for some of these applications, it's sufficient that the molecules just be electric dipole moments. But for many of these applications, you need different sorts of molecules. For example, to study ultra-cold chemistry, you need lots of different kinds of molecules. And for many applications, you would like molecules with an unpaired electron spin, things like looking for the electron-electric dipole moment or simulating quantum magnetism. So there have been a range of techniques developed to address these different needs. In many ways, the most successful has been what I think of as assembly of molecules from ultra-cold atoms using Feshbach resonance and transfer to the ground state. Again, the pioneering experiments from Gilla and around the same time with cesium-2 at Innsbruck have really been a huge stimulus to this field. But it's worth pointing out that in terms of dipole-dipole interactions, KRB is sort of an outlier among molecules. It has an exceptionally small electric dipole moment, so the dipole-dipole interactions, while still stronger than for atoms, are not that much stronger. And in addition, KRB is subject to chemical reactions with itself. So doing experiments with a bulk gas of KRB has been extremely challenging. It tends to just react with itself and go away. There's really a new era beginning now where it's going to be possible to explore in the regime of quantum degeneracy very strongly dipolar and also chemically stable gases. So we'll hear in the last talk of this session from Simon Cornish about the experiments using rubidium-cesium molecules at Durham. There's similar results from Innsbruck, from MIT. Martin Spherlein mentioned this briefly yesterday, also from Hong Kong, and a good handful of other experiments that are being built and coming online soon in this area. So this is a very exciting development in the field, but I'll leave it to Simon to tell you more about that. Instead, I'll focus on an alternate set of cooling techniques, which we think of as direct cooling. And these techniques are much more broadly applicable to different kinds of molecules. We don't need to be able to take alkali atoms and bind them together. In principle, we can start with many different kinds of molecules and cool them. And this is useful for many applications. There's been a development of this over the last 20 years or so using techniques like buffer gas cooling or Stark deceleration. But what we and many other groups have been pushing on over the last few years is to extend these techniques to the regime of higher phase-space density using methods such as laser cooling, evaporative cooling, and hopefully in the future, near future, sympathetic cooling. So the rest of my talk, I'll really focus on laser cooling. So it's not surprising that laser cooling of molecules is probably going to be hard. And why is it hard? Well, for atoms, well, in any case, what we need for laser cooling is a closed cycling transition. And for atoms, it's very simple to generate. Here's the sort of canonical picture. You excite an S to P transition. Every time you scatter a photon, you return to the same state, so you can scatter as many photons as you want without causing trouble. By contrast, if you try to do this with a molecule, because of the rotational structure, you immediately see that you're going to branch into at least 2 different rotational states just from selection rules, ordinary electric dipole selection rules. In addition, there are vibrational states in the molecule, and an excited state of the molecule in general can decay into many different vibrational states. And here there are no selection rules. There's simply numerical factors called Frank-Condon factors that determine how many vibrational states you can branch into, and typically the answer is many. So it's very hard to imagine scattering the huge number of photons needed for cooling and trapping, or at least it was until recently. So here's that same picture, decay into many vibrational levels. And a key advance was a seminal paper from Mike DeRosa back in 2004, where he pointed out that for a handful, but a large handful, a few dozen types of diatomic molecules, you only need a few repump lasers, not dozens, but a handful of repump lasers. And that's because the decay into excited vibrational levels is increasingly suppressed in these good species. So we use strontium fluoride molecules. Strontium fluoride is, it's got a single valence electron around a tightly bound core. It's sort of like the rubidium of the molecular world. And you can see in strontium fluoride, we can scatter about 50 photons on the main cycling transition before we decay into this first vibrational level. If we add a single repump laser, then we can scatter about 2,500 photons before we decay into this level. Another repump, and we can scatter about 10 to the 5 photons, which is enough for most experiments. But if you want to get fancy, you can add one more laser. So with 1 cycling laser and 3 repumping lasers, you can scatter more than 1 million photons in strontium fluoride. And that's enough for nearly every laser cooling and trapping experiment. Also notice that all these lasers are convenient diode-accessible wavelengths, so this is technically not so hard to imagine having 4 lasers rather than the 2 that you usually need for trapping alkalis. Another trick which has been important was pointed out by Juni's group in 2008, which is to avoid rotational branching, you can drive from a state with angular momentum 1 to a state with angular momentum 0. Then selection rules ensure that you only go back to the original state you started from. So don't cycle from the ground state, cycle from the first excited state. And that's very convenient, but it does cause some problem because for any given laser polarization, there are always dark Zeeman sublevels in this lower state with a larger angular momentum than the excited state. So in order to get cycling, you need to remix these dark states into a bright state. We've done this in a number of ways, we and others in the field. For example, if the molecule is magnetic, you can apply a magnetic field and use Larmor precession to precess dark into bright state. You can rapidly switch the laser polarization so that you address the states that used to be dark. And you can use the fact that it's a molecule and connect the different states via microwaves and a rotational, dissonant rotational state. So all of these work well. Another issue which we didn't realize until we were really doing experiments is that there's the extra levels in molecules lead to reduced scattering rate and therefore reduced optical forces. So in a 2-level system like an atom, we all know well that if you drive it hard, you equalize the population, and the maximum scattering rate and the maximum force is proportional to half the decay rate of the excited state. But in something like the system I just described, it's not hard to work out that the maximum rate that you can scatter photons occurs when you equalize population between all of the sublevels involved in the cycle, and that leads to a reduced scattering rate. Now, instead of half of the rate that this state decays, the maximum rate of scattering photons is 1/4 of the rate at which this state decays. And for technical reasons, we also repump our first vibrational level through the same common excited state. That means that the population gets spread out even further and the scattering rate is down by another factor of a few. So the bottom line is that the force, radiative force in these molecular experiments is always reduced compared to what it is in atoms by factors of anywhere from 2 to 4. Because of that, it's important to start with molecules that are going pretty slowly. All of our experiments are based on the technology known as a cryogenic buffer gas cooled beam developed in John Doyle's group. The idea is that we pre-cool molecules in a cryogenic buffer gas, either helium or neon. That gas streams through a cell and extracts molecules to form a beam. The bottom line is that these beams are quite slow, less than 200 meters per second. They're cold. The internal temperature is in the range of 1 to 4 Kelvin typically, and the brightness of these beams is dramatically higher than any other source that was previously available for the sorts of molecules that are of interest in these experiments. Okay, so I've been describing our system in this sort of toy model of having a state with angular momentum 1 driving to a state with angular momentum 0. But real life is not that simple. Strontium fluoride has an unpaired electron spin. It also has an unpaired nuclear spin from the fluorine, a spin 1/2. So the reality is there's spin rotation and hyperfine structure with the ground state having 4 sublevels split by some tens of megahertz. The excited state has substructure, but it's unresolved. And to deal with this, we simply, every laser in our experiment has RF sidebands applied to hit these 4 transitions at the same time. So it's technically not so difficult, but it turns out to play an important role in some of the experiments. So some very old but critical data showing for the first time optical cycling in a molecule. So here we're applying a pumping laser that should allow us to cycle if we have remixing of the dark states. So you can see if we apply a magnetic field to remix the dark Zeeman sublevels, we get more fluorescence as molecules pass through a laser beam. And then if we add a repumping laser, we get a lot more fluorescence. That means that here we were limited by cycling about 50 photons before we decayed into this state. Adding the repump means that we can scatter many more photons. And we take this for granted so much in atoms that it's worth emphasizing that optical cycling at this level is really crucial for making it possible to do efficient detection via fluorescence, to do imaging of fluorescence, imaging of absorption, and something else which is a nice feature for many experiments is this allows you to do efficient rotational cooling, which is just a fancy word for optical pumping into a single rotational level. Again, Boltzmann distribution usually populates a good handful of rotational levels, and this sort of optical pumping technique can enhance the population in a given level for doing an experiment. So using this optical cycling, we then went on to demonstrate that it's possible to apply forces to molecules. Here's an old experiment with a molecular beam traveling from left to right. Transverse cooling beams pushing from the top and the bottom on the beam to try to compress its velocity distribution. This is a very long interaction region because the scattering rates are so low in molecules. And then at the end, we imaged the fluorescence from the molecular beam with a probe laser here. And here's what typical data looks like. For the unperturbed beam, we see a transverse shape of the molecular beam shown in black. When we detune our lasers to the red to do Doppler cooling, we see very clear evidence of compression of the velocity distribution, which downstream leads to compression of the spatial distribution. And this gave temperatures of about 5 millikelvin. We also saw a form of Sisyphus cooling. This is a well-known effect, the same Sisyphus cooling effect that's used in gray molasses and some older experiments, but it only works when the lasers are blue detuned. And this got us to much lower temperatures in one dimension. Just to give you a sense of scale, the ultimate temperature here was interaction time limited, but the Doppler temperature limit for strontium fluoride, it's about what it is for alkalis, about 200 microkelvin. And I'll point out this sort of transverse cooling has now been demonstrated with quite similar results at Gila, at Imperial College, and at Harvard, and I know a few other groups are working on this now as well. So again, in some sense, this was the first demonstration that it's even possible to do laser cooling on a molecule. But I'll also emphasize that the act of transversely cooling a molecular beam is very useful in and of itself. This is a way of brightening the molecular beam and delivering more flux downstream for precision measurements, such as EDM measurements, and for loading traps downstream as well. Okay, so with that in mind, we were interested in seeing if we could trap the molecules, but we know that to trap them, we need to slow them down. There's a problem is, again, these dark Zeeman sublevels play a role in almost everything to do with laser cooling of molecules. It means that the standard technique of Zeeman slowing fails. And instead, we fell back on an old technique from the atomic physics community known as white light slowing. So the idea is to account for the changing Doppler shifts as molecules slow down. We have a broad range of frequencies. We'd like to have a very sharp frequency cutoff so that when the molecules hit a specified low velocity, they stop getting slowed by the laser. The way we do this is we send our lasers through a fiber EOM and drive it very hard to apply many sidebands. Here's what we actually see. And it has almost this top hat profile, but a little edge which causes trouble for us. Nevertheless, this does work. We take our molecular beam and push on it with a counter-propagating laser beams, this time with one cycling laser and two repumping lasers. And here's typical data. This is the longitudinal velocity distribution from our cryogenic beam. You can see it's peaked around 120 meters per second. And when we apply laser slowing, we clearly see an excess of slow molecules. And for us, the most interesting thing here was the excess of molecules at extremely low velocities, below the level where you can imagine capturing into a MOT. Right, so it's worth pointing out, though, that this white light slowing technique is quite inefficient in terms of delivering slow molecules to a trap region because the final velocity is not correlated with the final position as it is for a Zeeman slower. So this slowing, longitudinal slowing remains, I would say, the weakest point in this whole program of molecule trapping and cooling, and good ideas are needed to find better ways to do this. Nevertheless, it's now been possible again for several other groups to do this sort of longitudinal slowing. Imperial College, Yale, and Harvard. And I'll just point out now over very recently these groups have been able to start seeing evidence of molecules at the very low velocities that are needed to start loading into a trap. Imperial College has really beautiful data, but I'll leave that for Mike Tarbit's talk in the next slot. Okay, so we have slow molecules. Now what we'd like to do is to load them into a magneto-optical trap. You can see we're just following the historical pathway of atomic trapping and cooling. And let's just remember how a MOT is supposed to work. For a simple atomic transition like an S to P transition, you set up a magnetic field gradient, counterpropagating orthogonally polarized laser beams. You detune your lasers to the red so they do Doppler cooling. And then you arrange the polarization so that, for example, an atom on the right here is Zeeman shifted into resonance with the laser beam, which is pushing towards the left to apply a restoring force. And the opposite happens on the right. So in both cases, the atom is pushed towards the center of the trap. The scattering is always preferred in the correct direction because of the Zeeman detunings. And of course, because there's only one ground state level, the system always returns to the same state where it can scatter again and again. So beautiful principle. But let's see what happens with this sort of inverted structure that we have for a molecule. So let's look at a molecule over on the right side of the picture here. Now we detune our laser to the red again, so it will do Doppler cooling. The Zeeman shift, in this case, is only in the ground state. So in order for the Zeeman shift to push us closer to resonance, we apply a sigma minus beam to push the molecule that's on the right towards the center, which is great, except for the fact that this state will now decay not only back to where it started from, but also to these other dark Zeeman sublevels. And in particular, if it lands in this sublevel for a molecule on the right of the picture, the only way to get back out of this sublevel is to scatter a photon coming from the wrong direction and give an anti-restoring force. So it turns out this was shown analytically back in the 80s that the net force on this sort of system vanishes identically. So it's far from clear that it should be possible to make a magneto-optical trap in this way. Nevertheless, it had been done with atoms using D1 lines. For example, Vanderlei Bagnato's group had demonstrated making a MOT on the sodium D1 line, which worked not very differently from ordinary MOTs on D2 lines. Despite the fact that there were several published results, the mechanism was really quite unclear as to how this worked until just a year ago, Mike Tarbit published a beautiful paper explaining how forces are generated in these systems. But we decided, it works, let's try it. So here's what the setup looks like. We have our strontium fluoride beam that's been slowed, as I described before. Then we have, in order to conserve the power in our laser beams, we pass a single beam and wrap it around the system for all 6 directions in the MOT. And each of these beams, of course, has many, many different colors, frequencies, and polarizations. To give you a bit of a sense of just how ugly it really is, here's the level structure of the ground state and the excited state of the molecule in a magnetic field. There are these 4 resolved spin, rotation, and hyperfine levels. All of them have different G factors. The excited state has a G factor of roughly 0 because of the molecular structure. So what we do is we pass a laser through an EOM to introduce these side bands. The first laser has sigma minus polarization, and you can see that that shifts us closer to resonance with the desired state here and the desired state here, but it shifts us further from resonance in the desired state where, for this particular sublevel where the G factor is negative, just like in alkali atoms. One of the hyperfine states has a negative G factor. So to fix that, we add another laser with the opposite polarization and with its detuning set so that it's a little closer to resonance with this state, which was otherwise causing a problem. Remarkably, this all works. So this scheme allowed us to get the first MOT of a molecule, and this is a fluorescence image from our MOT. But if you look at this, you can see immediately, compared to normal MOTs, this is big and fluffy. The temperature is reasonable, but not very low. The lifetime was very short. And basically what was happening is this trap was so incredibly weak that the molecules were constantly boiling out over the edges of it. Nevertheless, it allowed us to get our foot in the door. And soon thereafter, Mike Tarbett, as he understood the forces in these sorts of MOTs, was able to suggest an alternate polarization scheme that gave us tighter forces. And I'll say a little about that later. But let me move on to what we've been doing recently, which is something that seems like the gold-plated solution to this, which is what we call the RF MOT. So the idea is that as you optically pump into dark states, instead of waiting there, what you do is switch the magnetic field and the laser polarization synchronously with each other to keep turning dark states into bright states as fast as you pump into them. Which sounds good, but it means that you have to be switching your polarizations and, crucially, your magnetic field gradient at megahertz scales to match the scattering rates. So the expectation here was that there would be greater forces, tighter confinement in the MOT from this technique. So our work really built on the pioneering work from Jun Yi's group, where they had demonstrated this sort of RF MOT method for transverse compression of a beam of yttrium oxide molecules. And in the meantime, John Doyle's group at Harvard had demonstrated making this sort of RF MOT work for lithium on the D1 line, where you can see here this RF MOT gave a much bigger trap signal than a DC MOT. So the main issue with creating this RF MOT is really a technical issue. So you're trying to modulate a magnetic field gradient of many Gauss per centimeter at frequencies of a few megahertz. The trouble is that you need to do that with coils that have a non-negligible inductance. We wanted our coils to be big enough to have large MOT beams for good capture velocities. And the combination of high frequency, high current, and high inductance means that we needed lots of voltage to drive these things. So to do this, we use a resonant tank circuit. To withstand the high voltage, we found some vacuum variable capacitors that were Soviet-era radio transmitter surplus devices available on eBay, which work very well. So getting this set up, what we expect is to have a confining force which works well when the phase of the magnetic field oscillation and the polarization switching are matched to each other. And sure enough, here's a fluorescent image from one of our first RF MOTs. And if we integrate this fluorescence signal as a function of the phase between the magnetic field and the polarization, we see a clear peak at 0 phase, as expected. So this RF MOT is working the way it's supposed to. And we went on to do standard measurements of the properties of this MOT. For example, we measure the temperature just by time of flight. Here's some time of flight images of the expanding cloud when we shut off the trap and let it freely expand. and then using the virial theorem, we can back out the confining potential here. So what did we find? Well, we found that, much to our surprise, both the trapping force, the spring constant, and the temperature of the MOT were basically the same for this RF MOT as they were for the improved polarization scheme MOT that Mike Tarbet has taught us how to do. So the promise of the RF MOT at first glance was not fulfilled. It looked no different. But what proved to be interesting was if we took this MOT and started turning down the trapping laser power, and the DC MOT went away almost immediately when we turned down the trapping laser power, but the RF MOT persisted to extremely low powers, and in the meantime, the temperature in the RF MOT plummeted as we turned down the trapping laser power, and this was quite unexpected. And I'll just point out that you can see very clearly we're able to produce MOTs with temperatures well below 1 millikelvin. So this was, along with simultaneous results from Gerard Rempa's group with a different method, this was the first direct production of molecules in the ultra-cold regime below 1 millikelvin. So we used this observation to do a sort of phase-space compression where we loaded the MOT at high scattering rate, where that allowed us to have good capture and a maximum number. Then once we had loaded the MOT, then we ramped down the power to a low power to get a minimum temperature. And if we do this ramp slowly enough, the transfer efficiency is basically 100%. And as we do this, the phase-space density compresses by roughly 3 orders of magnitude compared to what we had in earlier DC MOTs. So that's really a huge advance. And here's the bottom line of what we had with MOTs up to our recent publication earlier this year. The RF MOT was giving us a few thousand molecules at temperatures of about 400 microkelvin, perfectly reasonable lifetimes of about 500 milliseconds, and phase-space density 1,000 times greater than anything we had been able to do before. In the succeeding months, we've been tweaking things up. We now are able to trap more than 10,000 molecules at temperatures of about 300 microkelvin, and with some compression to get the phase-space density up to about a factor of 20 compared to what we had a few months ago. So this is now starting to be in the regime where you can really do experiments of the type that we're used to in atomic physics. So one of the things that we've done just in the last few days is to take our molecules from the MOT and load them into a magnetic quadrupole trap, a conservative trap. So we follow a very standard procedure. We load our MOT, we cool it and compress it. Cool it by ramping down the power, compress it by ramping up the magnetic field gradient. Then we switch off the MOT and switch on a large DC magnetic field gradient to create a static quadrupole trap. Hold for a while, and then take a fluorescence image of the resulting molecules. And here's data hot off the presses, 24 hours old, that shows the first magnetic trapping of strontium fluoride, where you can see after an initial transient, some of the molecules didn't get grabbed, but then after that transient, they're held in the magnetic trap with a lifetime of about 400 milliseconds. This is very early days, but this looks like an extremely promising step towards sympathetic or evaporative cooling of strontium fluoride and really pushing towards the regime of quantum degeneracy with these molecules. So with the advances that have been made in our group and in many other groups now over the last few years, there's a lot of excitement about possible new directions with laser-cooled molecules. So for example, there's a really lovely proposal from Shininoye pointing out that it's possible to do this sort of cooling on narrow lines that are accessible in most bialkali molecules. So the bialkalis are near quantum degeneracy, but still there's not been a quantum degenerate gas in molecules. This narrow line laser cooling may be a useful step to push to even lower temperatures with these bialkalis. We'll hear in the next talk from Mike Tarbet about ideas for using laser cooling techniques as well as rotational cooling and optical cycling to do better precision measurements, such as an electron EDM experiment, but there are lots of possible applications in this direction. In some sense, I feel like this is the low-hanging fruit for these techniques, is to improve precision measurements with molecules. There are also ideas for doing things like creating more complicated molecules via photoassociation. There's been tremendous excitement, I'll say a little bit more about this later, with the realization that it's possible to apply these and similar techniques, not just to diatomics, but to polyatomic species. Things such as, well, this, whatever that is, calcium, methyl something. There are ideas, for example, to, if you take laser-cooled and trapped strontium fluoride, if you can gently dissociate it, maybe that's a way to make ultra-cold fluorine. And other, this may prove an interesting indirect way to create ultra-cold samples of atoms that are otherwise impossible to make. And I'll just point out, many of us are excited about ideas that have been put forth by Hal Metcalf and also Ed Eiler for doing laser slowing and cooling without cycling transitions using stimulated forces, but that's a topic for further discussion. Let me just say a bit more about these two applications. So for polyatomic species, I can't talk about this field without mentioning the absolutely beautiful work from the groups of Gerhard Rempe and Martin Zeppenfeld at MPQ, where they've used a completely different paradigm for laser cooling of molecules, where instead of free space laser cooling like we're used to for atoms, they do in-trap Sisyphus cooling. With these techniques, they've been able to get down to temperatures of 400 microkelvin with very different sorts of molecules, things like methyl fluoride and whatever this is. Yeah, so molecules that are complicated enough that physicists have to think for a while what they're called. Right, so this is an important direction in the field which is related to but sort of orthogonal to what I've been telling you about. But in the meantime, the more standard laser cooling, just free space laser cooling like we do with atoms, now John Doyle's group has been pushing this towards polyatomics. So here's some recent data that I believe was shown in a poster earlier in the week, where they've demonstrated 1D transverse cooling of a beam of strontium hydroxide, a triatomic molecule. And you can see this data looks a lot like our data for strontium fluoride. They've done Sisyphus cooling to get temperatures down to 600 microkelvin. And I find this really astonishing and surprising that this technique is working even for triatomics. And there's John Doyle's group and one other group are now publishing papers suggesting that this basic method may work for much more complicated molecules as long as they have a crucial bit, which is this strontium oxide or similar calcium oxide bond. So this is a surprising and very interesting development. On our side, we've been pushing on working on a different species, laser cooling of thallium fluoride molecules. And thallium fluoride is it's an interesting molecule. It's different from the ones we've had before because it doesn't have an unpaired electron. It has a closed shell. But it turns out, in collaboration with Larry Hunter from Amherst College, we've been able to measure Frank Condon factors and lifetime of this state. So this transition looks like it's eminently viable for laser cooling. It has all the right properties. There's a bit of bad news, which is that all the wavelengths are deep in the ultraviolet, but more and more that's not a crippling disability these days. But the reason that we're interested in this really is that thallium fluoride turns out to be a very, very nice molecule for studying the nuclear shift moment, which you can think of as essentially equivalent to the nuclear electric dipole moment. So time reversal violation, similar to what Jerry Gabriel's talked about for the electron with our ACME experiment. So using thallium fluoride and techniques based on the sort of laser cooling methods that I've talked about, we're projecting a 30-fold increased sensitivity to this time reversal violating fundamental physics compared to the state of the art, which is from the Seattle Mercury 199 experiment. And this would really allow us to probe, again, now with hadronic physics, energy scales far above what's accessible at the LHC. So I'll point out that all the work has been done by a really fantastic team of graduate students and postdocs, and point out in particular the work of my postdoc, Danny McCarran, who's been on the team since before our first MOT and has really been a tremendous leader. And also we've had really invaluable contributions from our collaboration with Mike Tarbett, who's worked out a lot of what's happening in the system as we do the experiments. So that's the end of my story. Just run through a quick summary and outlook. We've shown that it's possible to do transverse laser cooling, which again has applications for brightening molecular beams. We've demonstrated that we can slow molecular beams enough to trap them. We've demonstrated magneto-optical traps, now down with sub-millikelvin temperatures. And we've just, in the last few days, demonstrated that we can take molecules from this mod and load them into conservative traps, just like we're used to doing with atoms. So what's coming next in this path, long-worn path for atomic physics is we are pretty sure we know how to provide substantially more molecules in the MOT, and we're going to work on cooling towards degeneracy. So I think really the key issue here is going to be whether it's possible to sympathetically cool molecules with some co-trapped atoms. And there's been some theory activity in this recently, but this is really, I think, the key step that needs to be understood. From my point of view, one of the most interesting things is that these methods are applicable to species that are useful for precision measurements, such as terbium fluoride for the electron EDM that Mike Tarbett will talk about, thallium fluoride for this nuclear shift moment or nuclear EDM that I mentioned, and others. And in addition, it looks like this is going to expand out to give access to much broader range of molecules, polyatomic species, in the very near future. So with that, that's the end of my talk, and I'll thank you for your attention.
Thank you, Dave, for this very exciting talk and also giving a nice overview. It's so nice to see the excitement, which is very similar to the one we had in the early 90s, by trying many, many different schemes and playing with all these laser cooling forces. So I'm sure there are questions in the room. Randy?
Hi, really nice work. What are the prospects for optical trapping strontium fluoride?
Right, so I would say there's no reason why it won't work. The issue at this point is that we need to get the phase space density up to load into the typical volume and depth of an optical trap. So we could trap something in an optical trap now, but it's because our temperatures are a little higher than we're used to for alkalis, the densities are a little lower, the traps are still a few times weaker. We're not ready to do it yet, but it's on the path. I would say once we can get the phase space up by another couple of orders of magnitude, then we'll try to optically trap them.
Other questions? Yes. Wolfgang?
Dave, wonderful overview over how broad the field has become. I'm intrigued to see that we have to rethink about laser cooling, because this is definitely a new challenge for laser cooling, and you made it really very, very clear. But there's one comment I want to make when you said laser cooling without spontaneous emission. This is not possible for entropy reasons.
Well,
unless you use non-classical light, the paper you cited is wrong.
So
we need spontaneous emission. We can get a lot of force out of bichromatic force, out of the stimulated force, but eventually we have to break the unitarity time evolution, which is conserving entropy by optical pumping or spontaneous emission.
So
there is no way around it, and this paper is wrong. It should not be cited.
Well, okay, so I should be clear. This paper is a hand-waving argument, which I would say my point of view on this was exactly the same as yours for many years, but now I've started to waver and to wonder whether there might not be some truth to this. What I can say is that if you look at the data, it's crystal clear that in the data there is cooling, and it's not so clear that that cooling is proportional to the rate of spontaneous emission. So I put a question mark because I'm not convinced, but I would say compared to 2 years ago when I would have said exactly what you're saying, I've started to wonder whether there's not a loophole that we're failing to take into account. But this is something I I understand the argument completely,
I've analyzed
though.
the paper very carefully and was in discussion with the authors. And the loophole is only when you use non-classical light. If light has a Hilbert space of many, many states, then you can put entropy into it. But the moment you use a laser beam, you use the C number for the light, and it has no entropy. This is really the distinction, and this is the loophole. And the data in the paper is, they have one spontaneous emission event during the cooling time, and this one photon could be enough. The data is completely inconclusive.
That I completely agree with, although earlier data, I would say there are very strong cooling forces that are not obviously related to spontaneous emission. And, well, I'd be curious to talk, because I think this is an extremely interesting question, and I wouldn't be surprised if you're right, but as I said, I've started to waver on it a little bit.
Well, what we can say, if I can add something, that when you use the stimulated forces, per spontaneous photon, you can remove much more of energy, and that's for sure, and this has been seen in the blue detune cooling, for instance.
Sure, absolutely.
With even 20 photons, you can remove a huge amount of energy.
Absolutely.
And this does not violate anything.
That's right. The forces, it's crystal clear that you can apply large forces.
But this is especially useful for molecules with bad branching ratios.
That's right. That's why it's an interesting question. If there's any potential loophole.
Spontaneous emission takes away a lot of kinetic energy. Yes.
Yeah.
Other questions? Yes.
Can you comment on the timescale with which you expect black body radiation to rethermalize the vibrational degrees of freedom?
Right. So it's been a little while since I've gone through those numbers, but the number that sticks in my head is order many tens of seconds for room temperature for strontium fluoride. If for molecules like hydrides, it tends to be much faster because the vibrational energies are closer to the peak of room temperature black body, but our vibrational energies are low enough that it's a smaller effect for us. But at some point it's going to start to be an issue, but not till some tens of seconds.
A last quick question. Okay, if not, let's thank Dave for this wonderful talk, and we move on. To Mike Tarbett from Imperial College, who will explain to us how this laser cooling works with this complicated polarization and laser schemes, which is a bit wonderful per se.